Welcome back. Right, in the previous two video we covered the support vector machine concept as well as the linear SVM classification, and also conducted an actual implementation of it. In this lesson we are going to move away from the linear SVM or linear kernel. We're going to start looking at polynomial kernel as we did when we were looking at the regression. Now, this is the powerful part about the SVM, is that it is able to actually take on other kernel, and later on you can even define custom kernel yourself. So in this part, what I'd like to show you is that typically, as we did see earlier with the linear, is that it struggled to actually separate certain points, such as this. What you can see here is that these are the Virginica, the red one being the versicolor. It just have difficulties. Well, no matter how you draw a straight line, it's just not going to be able to segregate these few points here. I mean, what you have here is these few points here, and essentially you basically need a line that looks like this to actually segregate these two classes. Basically, they are in between each other. There's no way that you can draw a straight line and actually be able to there's no way that you can actually draw a straight line, full stop. Right, so let me discard that. Okay, so earlier I did actually click onto this link. I'm gonna show you that right now. I've opened it up but never really did actually run that through. I'm gonna show you that right now. So let's come over here. So this is what we have in terms of the support vector machine that is implemented by Kapathy. Now, I mentioned before, Kapathy was the professor in Stanford. He is now working for Tesla in their AI research portion. Right, so what we want to do is that I'm going to toggle this. Right now, this is, you notice that this is obviously not a straight line, so this is clearly not linear. Now, when I actually switch it over to linear, this is what you have here. You have a couple of different classes. You have the green, all right, and you have the red. And there's a one green here, which obviously is, well, a clear violation. All right, and what you have right now is that the linear kernel is obviously struggling to segregate between the two. And now recall that there are a few things that we can actually do here. You can actually have this set the C, but we won't leave that for now. The idea here is to actually illustrate the difference between the linear as well as the Redal, which is non-linear kernel. The RBF is not too dissimilar to the polynomial, which is obviously non-linear. Okay, so I'm just going to toggle this by pressing K, and what you can see here is that with a non-linear, it can obviously clearly segregate between the green dots as well as the red dots. Okay, so now with this linear, it's not able to actually segregate them. Now you can play with this a little bit more but you can actually provide more mouse clicks. By doing more, what you're actually doing essentially is creating more samples. These larger circle here are the support vectors. All right, there's a funny support vectors here clearly, and I can add more green dots by pressing Shift. And you can see here is that the closer ones are the support vectors. Okay, the further one just stay the normal size, and this shows you the number of support vectors is 12 out of 59. You can of course add more, especially increase it like this way. Okay, so I hope that is actually helpful. Let me just toggle it once more, and this is now the non-linear, and clearly you can see that it actually can segregate the two classes really well. Now what happens if I actually press some red one here? Okay, so you can see that it still is able to actually segregate them. All right, so that's really the power of non-linear kernels. Okay, so let's come back here. We were looking at this portion. the polynomial. I just want to explain a little bit how the polynomial portion actually works. Now, if you look at the polynomial kernel, what you have here is this. The linear is just not able to segregate. What we have is 4 purple circles and 2 here and 2 brown circles. No matter how you actually draw within a one-dimensional, there's no way that you can actually segregate them at all. It's inseparable. So what you can do is that you can actually transform this using the polynomial kernel. Oh, there's actually a typo here. It should be kernel, not K-E-N-A-L. It should be K-E-R-N-E-L. Okay, so with the polynomial, what you have done is that you have transformed it into a hyperbola where you can actually segregate it using these and these here. Alright, so that's really the basic idea here, is that you transform from here to here by using the polynomial kernel. That's how you actually segregate the classes. And if you can picture it, you can actually go from 2D to 3D as well. That's essentially how support vector machine works, and able to actually transition it to a higher dimension in order to segregate the classes. Alright, so we're going to implement polynomial support vector machine. Again, we're setting the C is equal to 1. The kernel we set to poly, the degree is 3, and C is equal to 1 here, and we're fitting our classification, all right, with the X and Y from before. Again, we're going to plot, and let you have a look here, is that recall that we have 3 different classes, the Setosa plus the other 2. Okay, so notice that there's a straight line here, and the polynomial is able to provide a non-linear segregation, although it's not able to actually completely segregate the 2, because there is a limit to 3 or cubic. Hence it's not able to actually segregate them. Obviously, if you increase it to 8, 9, it will most likely be able to actually segregate this really well. But then again, you might actually have a situation of overfitting. And you have these 1 misclassification, 2, 3, 4, 5 misclassification. Alright, so that's really the basic idea of polynomial. Right now, we're going to implement this onto the iris dataset. And we want to compare this polynomial implementation against the linear, which we're going to use as a baseline. Again, we're doing the same. We're going to have a test train split. We're going to run standardization or scale it. Again, we're converting the string into classes and basically splitting this with the train size of 80 and leaving 20% for our training. Right, we're fitting our X and run our the polynomial kernel fitting. It didn't take very long, and let's see within the training set what our cross validation looks like. So the accuracy is 0.9524. Let's come up here and have a look at the for linear, 0.9524. So the polynomial is better. However, the standard deviation of linear is lower at 5% versus 7%. Okay, so although the polynomial accuracy is higher, the so-called the score fluctuates quite a fair bit. So we're going to run the confusion matrix, and you can see that there's 6 errors here, which we actually identified earlier. There are actually 6 errors here, and but this is a bit different from the previous score there. Okay, so let's have a look at the precision score, the recall and F1. The precision score is 95%, and which is not too dissimilar to the accuracy. The recall and F1 are all pretty good. Now let's have a look at the out of sample, or the test data set, to see how does the polynomial actually perform, polynomial kernel perform in the test data set. Again, we're going to have a cross-validation of 3, and we also transform the x-test data. And let's have a look at the confusion matrix. Looks like this only has 3 errors, okay, 3 mislabel class versus 2 here. Well, unfortunately, the polynomial underperform in this case as far as the confusion matrix is concerned. So let's look at the precision score, recall score, and F1 score. Looks like they are all lower across the board when you actually look at the compare against the linear. And that's a problem, okay? And what you really want is that the performance to be better, if not better than the linear. Otherwise, well, when you use the nonlinear polynomial. And what you can see here is that there's one conclusion you can draw from the polynomial kernel, is that it has wide or rather has large variance. Recall what we covered in the past on the lesson of cross-validation, as well as looking at the curve itself. Recall from the lesson that we cover under variance bias trade-off. I'll just pull it up from my GitHub. I've posted it here. Under the variance bias trade-off, I'll just walk through this. If it's a good, this is a good what you call variance bias trade-off. There's accuracy is high. The training as well as the test are very, very close to each other. Under variance, your accuracy, although high, but the training and test, the so-called difference is very high. In essence, this is really an example of high variance. And if you look at the finally the high bias, whereby the actual result of the training and test has really low accuracy. But in this case, what we have is this problem. The training and the test has a wide fluctuation, has a completely different performance. We have a situation whereby the training score, right, within the training score is 95, but when it comes to the actual out of sample, it drops substantially down to 91. Whereas if you compare this against the linear, the so-called precision, recall, or even F1 is not too different from each other when you compare to the polynomial kernel. Right, so that's really the end of this lesson on the polynomial kernel. Before we move away, I'd like you to actually try 2 things. I want you to actually try them separately rather than combine, because if you combine them, you might not be able to tell which is actually causing the issue. So the best thing to do right now is I'd like you to again change the C to 0.01. And the next thing is change the degree to 5. Okay, so change the degree to 5 and see what is the actual outcome of varying the degree itself rather than cubic. Have it at a higher polynomial and see how does it actually impact or have an impact on our performance. Remember to record the score of 95% within the actual training sample. And with that, I'm going to ask you to pause the video. When you come back, I will summarize the lesson, and we'll talk about what's to come in future lesson. Welcome back. I hope you actually try that out by varying both the C itself as well as the degree itself. What I did is that I went one step further. I changed the degree, our polynomial degree, to 10, and I'll show you the score. Notice the score drops substantially, and there are lots of errors on both in terms of the inaccuracy, the precision score, across the board, all the score drops substantially. Right, so really what we have covered in this lesson is the actual polynomial. The advantage of it really is that it is actually able to fit to non-linear data as we have here. Unfortunately, it didn't actually work that well this time around, and we implemented the polynomial SVM, and we tested out in and out sample and compare against the linear implementation of SVM. So when we come back, we're going to go into Gaussian radar basis function, which you saw earlier when I actually demonstrate to you using Carpathy's website. And I look forward to going through the RBF function with you, and I'll see you then.